Okay, so let's go on to the notion of order. So order and ordered fields. So okay, so order is something that you're familiar with. So given a set S, we call a binary relation which we'll denote like this, an order. Okay. So the order is basically based on the notion, back in the rational numbers, you have the notion of greater than equal to, right? Less than equal to, greater than equal to. Okay, so we're just going to generalize this to fields. Okay. So we call something like this an order if it satisfies basically what this symbol normally satisfies. Okay, so if one given any A and B in the set, either A is less than equal to B, or B is less than equal to A. So you have to have, if you take any two elements, they should be comparable to each other, right? You need some way of they have to satisfy one of these relations. Okay. So this property is called totality. Okay. And this is the proper name of this is a total order. Okay. Second property is if both of these things are true, if A is less than or equal to B and B is less than or equal to A, then A and B must be equal. This property is called anti-symmetry. Property number 3 is that if A is less than or equal to B and B less than or equal to C, then A must be less than or equal to C. It's called transitivity. Transitivity. Okay. Examples are with the standard less than or equal, right, is definitely a set with an ordered set, right? And we call S with this order an ordered set. Okay. B, if you take the Oxford English Dictionary and you use the lexicographical order, right? That is a set with an order, right? The alphabetic order, right? So you say, one word is bigger than the other word if it occurs later in the dictionary, right? So, right. So definitely, anytime you have two words, one is later in the dictionary, right? If they're later than, if there's this relation, then they must be the same word, and certainly if you've got one word that precedes another and another word precedes another, then the first one precedes the last one, right? So any dictionary with the alphabetic and lexicographical order is an ordered set. The complex numbers, right? Complex numbers, right? Things that look like A plus BI, where A and B are real numbers. You can put on it also lexicographical order. Okay, so you say, right, that A plus BI is less than or equal to C plus DI if A is less than C, right? Or if A is equal to C and B is less than or equal to D. Okay, so if I have 1 plus I, that's less than or equal to 2 plus I, right? 1 plus I is less than or equal to 1 plus 2I, right? So they have this. The first letter is equal, but this guy's second letter is before this guy's second letter. Yes, Nick.
How does it rank? Like you had 1 plus 8I relative to 8 plus 1I.
So the 8, you look at the first letter first, right? So 1 plus 8I and 8 plus 1I, 8 plus 1I. So you say, well, look, the real part is less than the real part, so this guy is less than. Okay. If the real parts are equal, then you look at the imaginary part. Okay, so it's just like, a dictionary where there's only 2-letter words. Right. A B is certainly less than B A, right? In the dictionary, right? So here's my dictionary. It has only 2-letter words, right? And complex numbers is just like that. It's a dictionary with 2-letter words. Okay. Here's a non-example. R2, so all sets, subsets of R2 with set inclusion as the relation. Okay, so I mean. This set with set inclusion as its order, satisfies some things, right? If I have one set that's included in another, A is contained in B, and B is contained in C, then certainly A is contained in C, right? So transitivity is fine. Anti-symmetry is also fine, right? If A is contained in B and B is contained in A, then A and B have to be the same set. Right? So anti-symmetry is fine. But you see that totality fails, right? I could have 2 sets and neither is contained in the other, right? So I've got set A and set B, but A is not contained in B and B is not contained in A, right? So this is not a total order. Okay. Okay. So that's what an ordered set is. And now we're going to talk about an ordered field. So if a field has an order, so given a field F, with an order, if for all A and B in F, A being less than or equal to B implies that A plus C is less than or equal to B plus C. So all A, B, sorry. Given any elements A, B, and C in F, if we have these 2 properties, one that when you add something to both sides, the order is preserved. 2, if you multiply both sides by an element bigger than 0, then the order is preserved. So if the order is preserved by addition and multiplication by an element that's greater than 0, then we call F an ordered field. Then we call F an ordered field. F with this order, an ordered field. So notice that a field that has an order is not an ordered field, right? You can't just have a field with an order. It has to be a field with an order, and the order and the operations of F interact in a good way, right? When you add something to both sides, the order has to be preserved. When you multiply both sides, the order is preserved as long as you're bigger than 0, multiplying by something bigger than 0. Okay. So for example, one of the homework problems, I think, is to show that there's no, C cannot be made into an ordered field. The complex numbers cannot be made into an ordered field. Okay. You see that we can put an order on it. Okay, we can put an order on it, the lexicographical order, but that doesn't make it into an ordered field, and in fact, it's impossible to. So
C
a
is
field,
not an ordered field,
C cannot be made into an ordered field. It's impossible.
but we can take certain parts and make it an ordered field.
I mean, R is included in C, and you can put you can make R an ordered field.
Okay.
Yeah. But you can't make all of C. You can't make C, the field C, an ordered
What's
field.
the difference between R squared and R?
R squared is the plane, right? So R squared is everything that looks like x, y, where x and y are in R. Right, so R is the real numbers. Right, R squared is pairs, x, y, right? So in other words, the plane, right? R cubed is x, y, z, where x, y, and z are in R. Right, just space, etc., etc. Okay. 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 Theorem. Properties of ordered fields. Properties of ordered fields. So let's say that F with an order is an ordered field. Let this be an ordered field. Then a bunch of things happen that you would think should happen. Okay. So one, if A is less than or equal to B, then negative B is less than or equal to negative A. 2, if A is less than or equal to B and C less than or equal to 0, then BC is less than or equal to AC. 3, if 0 is less than or equal to A and 0 is less than or equal to B, then 0 is less than or equal to AB. 4, 0 is less than or equal to A times A for all A. That's obvious. Number 5, 0 is less than 1. Yes?
I think for number 2 you flipped shouldn't AC still be smaller than BC?
No, because C is less than.
Oh, sorry, I didn't see that one.
C is less than or equal to 0. Yeah.
Professor,
Yeah.
are you saying or and?
Where?
So for all of these, you said these are properties of an ordered field. So if that's an ordered field, then
All these things are true.
All of those.
All these things are
Okay.
true. Yeah. Then let this be an ordered field. Then the following are true. Okay. And then there are a couple more. 0 less than A implies that 0 is less than A inverse, multiplicative inverse. 7, 0 less than A less than B implies that 0 is less than B inverse is less than B inverse. these are all consequences of the definition of an ordered field. And just like when we had the field axioms, and then we had a bunch of consequences, we've got an ordered field, then you'll have a bunch of consequences that we include. Yes, Nick?
Is there ever a situation where 5 is not true? Like, is that something that we have to add as like a result of an ordered field?
Yeah.
We'll have times where 1 may not be greater than 0.
Well, I mean, it
seems almost like then if we do that, we should also say like we should throw in addition and like kind of that seems like almost one of the fundamental rules that like we kind of hold for any situation.
but it's not immediately obvious, right? It's not immediately obvious. You have a field, right? A field is just this thing that satisfies some axioms, right? And then you put an order on it, right? The order, there's nothing in this definition that instantly says that 1 has to be greater than 0. Maybe 1 is less than 0, right?
Yeah.
Right? There's nothing in the field definition or in this definition of order that says 1 has to be less than 0, 1 has to be greater than 0. So we just stated. Yeah.
Wait, so does that imply like if you have something that's mod 3, that then 3 would be less than 2 because 3 is 0?
So the question is, can you put an order? Can you make that into an ordered field? Right, and the answer is no. Right. Right, because it's right, because everything is less than equal to everything else. Right. You can't put an order on it. Okay, so let me just prove a couple of these. Again, the proofs are not exciting. Let's prove the first one. If A is less than or equal to B, then negative B is less than or equal to negative A. Well, you say, okay, well, say that A is less than or equal to B, then A plus negative A plus negative B is less than or equal to B plus negative A plus negative B. Okay, and so this is by property 1. In the definition. In the definition over there of the ordered field, right? You add the same thing to both sides, the order doesn't change, right? Okay, and then you see what's going to happen, right? You use the associative property, A plus negative B is less than or equal to B plus 1. I guess you commute also. B plus negative B plus negative A. So you're using associative and commutative properties. And then you get 0 plus negative B is less than or equal to 0 plus negative A by definition of additive inverse. And then you get negative B is less than or equal to negative A by definition of the additive identity.
Why don't you just combine those two steps, associative and commutative?
Yeah.
Okay.
Yeah, being sloppy. Okay. Let me just put one more up. Let's do number 2, right? That if A is less than or equal to B and C is less than or equal to 0, then BC is less than or equal to AC. Say, okay, well, if A is less than or equal to C, then A times negative C is less than or equal to B times negative C. Right, because 0 is less than or equal to negative C. by 1, actually. By part 1. Okay, so here I'm using the second property, property 2, part 2 of the definition of ordered field. Right? I'm multiplying by something bigger than 0. Multiplying by something bigger than 0. Now, I know that c is less than 0, so by part 1, negative c is bigger than 0. Okay, so, and then I'm multiplying by something bigger than 0, and so the order doesn't change. I use that property of the ordered fields. Okay, so now, that's the same thing as saying that negative AC is less than or equal to negative BC. Okay. And for this, we have to use the homework problem that 2 people put up, right? That A times negative C is the same thing as negative AC, right? So this was the, this was 3 in the previous theorem, the earlier theorem. Okay. And then, by part 1 again, we get that BC is less than or equal to AC by 1 again. Right? Remember, part 1 said that you multiply by negative. If you take the added inverses, then you change the direction. Yeah, all right.
So in a theorem, you're allowed to use the previous property of the same theorem? but you're not
Yeah,
allowed
because
to
we
use-
already proved it.
Okay, but you're not allowed to use something below it?
Well, not if you use this property to prove that property, prove that later property, right? If I use this to prove that later, I can't use that later property to prove this now because that'll be circular reasoning, right? So, I mean, if you found some way to prove a later fact directly, and then you say, I'm going to do this one, I'm going to prove this one, and then I'm going to prove this one, and then I'm going to prove this one. As long as your order is okay, is sound, that's fine, right? It doesn't matter. But the way they're laid out in the book, each one implies the next one. That's how they laid it out. Nick, do you have a question?
You just answered it.
Okay, that's it for today. If you didn't turn in your homework, please do, and I'll send out a new assignment later.